everyone, and thank you for attending today's lecture series. My name is Chris Hinet, and I am the Global Pre- and Post-Technical Sales Manager at Molex Connected Enterprise Solutions. In today's webinar, we will take 60 minutes to focus on smart buildings and zone cabling. For the best viewing experience, we recommend using a wired internet connection and closing any program or browser sessions running in background that could cause issues. As usual, this session will be recorded for knowledge sharing purposes and will be available later for on-demand viewing. And depending on your level of participation, your voice, picture, and/or video may be captured as part of the recording. If you choose to not participate in this recorded session, please feel free to exit at this time. For those of you participating in this session, and as is the case with any meeting or communication method, please practice careful communications. Also, please note that I will mute all lines at the beginning of this lecture series. So should you have any questions, please do not hesitate to stop me, raise your hand, and if I see it, I will unmute your line. Or Mike as well may also let me know somebody has a question. However, please do not use the chat box as it is slightly disturbing when you are the presenter. So here's the agenda for today. Basically, what we're going to do is we will split this presentation in two parts. In the first part of this presentation, we will talk about smart buildings. And in the second part, we will try to create a design and a complete bill of materials for a smart building using an active zone cabling. And we will also do it with a conventional cabling that will allow us then to make a comparison between the two. Okay, so we have a lot to cover today, so let's kick off. Right, so let's start by defining what is a smart building or a digital building, or is there even any difference between the two? Well, as its most basic, a smart building is one that is using technology to share information between systems about what goes on in the building with the objective to optimize the building's performance. This information is then used to automate various processes from heating and ventilation to air conditioning and lighting, etc. Then this is when comes the importance of IP convergence. Indeed, IP convergence is what will enable the main features of the smart building. So why is this important? Well, simply because the only thing worse than being blind is having sight but no vision. You cannot manage or plan your building effectively if you cannot see or cannot control what you have. Visibility and control are of essence. Without this accurate view, control, or intelligence in your building, management decisions can be made based on bad or corrupted data, resulting in bad decisions. Another important thing about IP convergence is that companies already have lots of information and documentation about their building in various systems, different systems or solutions to manage and control their buildings in various applications and for different purposes. And the issue is that they keep accumulating this documentation and they still add different layers of building applications, but they don't use them all the time, simply because it may not always fit the purpose. As a result, they are looking for a way to replace their system or to reduce the amount of documentation they have to maintain, because in the end, they are not sure anymore whether they can trust what they have. And let me tell you, not only the cost of bad data can lead to bad decisions to be made, it will also lead to expensive decisions being made. When facility managers make such decisions, they are based on the inaccurate picture of what's in their building and consequently a false perception of the situation. So what are the main features of a smart building? Sorry. Well, to start with, systems are connected. The most fundamental feature of a smart building is that the core systems within it are linked. So water meters, pumps, fire alarms, power, lighting, etc. are all connected. This is what makes a building smart, the ability of the systems within it to talk to one another. Then the use of sensors. Sensors are an integral part of smart buildings, and they play an important role in collecting data to make informed decisions about where to allocate resources. So for example, footfall counters may be integrated in the building to provide information on where people are at certain times of the day and which areas are high traffic. Then automation. Information is gathered and analyzed by the systems that have been put in place in a smart building. Importantly, this is done constantly and in real time. This ongoing monitoring allows for automated adjustments that can control conditions across an entire building. And finally, data. Smart buildings generate a large volume of valuable data about their own use, which is something that regular buildings simply don't do. Now, at this point, we can also talk about digital buildings. Let's now have a few words about the importance of keeping control of your building. Control helps you move away from what I usually call the silos of chaos. This is when the information is stored in different places, building controls are managed by different systems, and all processes are based on human intervention. With dumb or standard buildings, most companies naturally gravitate toward the silos of chaos. And it's easy to let it happen, but it doesn't create a scalable foundation. This is why IP convergence provides valuable information to assist facility managers in many ways. Because eventually, how can you control and secure your building if you don't know what you have? As I'm usually saying, the truth is that you cannot have high standards without good discipline. Now, to continue with this overview on smart buildings, let's take a look at 5 concrete benefits. To start with, smart buildings make the occupants more productive. Air quality, physical comfort, security, sanitation, hey, very hot topic at the moment, lighting, and even room and space availability can all be delivered at an optimum level to enable occupants to perform well and better. Then, smart buildings help reduce energy consumption. Smart buildings are greener, more energy efficient, and more cost effective. Smart buildings also eliminate guesswork. The use of sensors and cameras provides precise data on how the building is being used, which can be converted then into insightful decision making. Space utilization can be improved based on actual data, as the building generates actionable automated reports, leaving intelligence automatically. Smart buildings also trigger significant operational savings. This includes the savings that can be made in terms of everyday spend and maintenance on equipment. It also extends to the potential savings that are offered by identifying underutilized resources and the potential for growth into unused spaces. Finally, smart buildings allow for better data protection. Equipment such as thermal sensors, PIR sensors, infrared sensors, they all measure data without identifiable images of staff or other public. So, IP convergence. IP convergence enables the sharing of resources across applications and provides high levels of standardizations, availability, reliability, and support for new deployments. Another key benefit of all IP networks is the improved safety. Unlike conventional field bus systems, IP has built-in safety features for authentication and access control. Also, in an all-over IP network, building management and technology-related devices communicate over Ethernet Internet Protocol with the building LAN, what we call Ethernet IP, providing the physical communication layer as well as power over Ethernet. And PoE is an essential driver for the uptake of IP convergence since it reduces the need for separate power cabling. For example, individual PoE-powered LED lighting fixtures, they all can be controlled via their own IP address. So IP devices and networks speak the same language, end to end. That means no translation is required between sensors and devices, servers, cabling, and operating systems. And conveniently, devices and systems that work with Ethernet IP technology are fairly inexpensive. Often, off-the-shelf devices can be used to digitally connect and control buildings. Also, introducing smart converged networks means new energy conserving technologies and applications as well that can be introduced, such as intelligent management of building space and resources. And because there is no theoretical limit to the number of devices that can be addressed, networks can be scaled up or down whenever required with relative ease, and devices can be added without affecting network performance or reliability. As an example, the current Internet Protocol version, IPv6, IPv6 can theoretically allocate more than 1,000 IP addresses per square meter, and also access control and authentication measures incorporated in IP. They will improve building automation security, which is essential when dealing with such a large volume of additional connected devices. Finally, reliability. Going all over IP also helps reliability because the star topology reduces the number of connection points, but also as a result of the high level of standardization, troubleshooting and resolving problems also becomes faster and easier. What's more, new applications can be developed quickly and easily thanks to the availability of data from different components. And administrators can integrate these with basically just a mouse click. So remember, on one hand, connectivity is the nerve of a smart building. On the other hand, a solution like the Molex coursing platform delivers a unique, cost-effective infrastructure incorporating distributed sensors to drive real-time energy usage reporting, room occupancy, light status, and environmental monitoring. The ability to migrate lighting and other unrelated building systems like meeting room management, audiovisual equipment, powered shades and emergency notifications to an orchestrated IP-based infrastructure creates business value and an asset for building developers and enterprises. Now, what do standards say about that? There are three main groups of standards that address intelligent building systems. You've got the traditional ANSI TIA standard body, and then you've got also ISO, IEC, and CENELEC, and finally, last but not least, ANSI BICSI as well. Now, I'm not going to spend too much time on these standards because they are all covered in great details in our latest standards updates technical built-in. in which you will find all the information you need to know about these trends. So, mostly because of this very nice, exciting, and sometimes scary smart building concept, many organizations are now rethinking their structured cabling because they want to make the most of their assets by integrating multiple different services, thereby maximizing flexibility and achieving cost savings. As we said earlier, these services include but are not limited to BAS, smart lighting, data, voice networks, wireless, Wi-Fi, energy management, visual information display, digital signage, sensors, actuators, HVAC controls, etc., etc. Note, however, that fire alarms usually are not considered as part of the cabling systems because for intelligent building, sorry, because they are usually installed separately for obvious reasons. So the demands we put on networks and data centers are only becoming more strenuous. Buildings are getting smarter, Internet of Things (IoT) is expanding, wireless connections are flourishing, data generation is continuing to grow daily. The way we designed and installed cabling and connectivity infrastructure in the past, even as recently as 10 years ago, cannot support what we now need: more speed, more bandwidth, and more power. And to ensure uptime, performance, and connectivity, the right design and connectivity are essential. More flexibility with cabling systems is now required because modern workspaces are continually being reconfigured. Let's not forget that the Internet protocol used for IP devices allows structured cabling systems to support multi-products and multi-environment. So, what is a zone cabling infrastructure? Zone cabling runs horizontal cables from patch panels in telecommunications room to a zone enclosure, ZE or ZE, which can be then located under a floor, in a ceiling, or on the wall. Connections in the zone enclosure are made using modular outlets or punch-down blocks. There could also be active equipment in the zone enclosure. And here's a flat view of a typical zone cabling architecture as opposed to a traditional cabling architecture. We will detail the different zone cabling options a little bit later in this presentation. So, zone cabling is ideal for supporting the convergence of data and voice networks, wireless Wi-Fi device uplink connections, and a wide range of sensors, control panels, and detectors for lighting, security, and other building communications. Let's now talk about naming conventions. The name of an intermediate connection point depends on the types of endpoint device connection it serves and on which of the applicable regional structured cabling standards it is based. It may be called Service Concentration Point or SCP, Horizontal Consolidation Point or HCP, or the well-known Consolidation Point CP. The most commonly used name is Zone Enclosure or Zone Box. The functions of a CP and an SCP or HCP can be combined, obviously, within the same zone enclosure. Now, the name used for the outlet depends on the types of connected device and on the applicable regional structured cabling standard as well. For building devices such as CCTV cameras, these will be a service outlets, SO, or equipment outlets, EO, For a voice or data device, it will be called a telecommunications outlet, TO. Now, is a work area outlet always required for data voice transmission and for building devices? Well, an outlet for data voice transmission is always mandatory, whether or not a zone enclosure is present. For building devices, an outlet is not required. Maybe scenarios where a typical 4-connector channel is not used when connecting some types of building devices, especially those that reside in the ceiling space where it is impractical to install a faceplate. Think of the IoT, for instance. Instead, there is just one patch cord in the telecommunications room, and the permanent link is terminated at the other end with a plug, so it can connect directly to the device, essentially eliminating the equipment cord. This creates what is now known as a modular plug terminated link, or MPTL. The use of a link that terminates to a plug and eliminates the equipment cord was first called out in the Big C005 standard, Electronic Safety and Security. It is now included in most of other relevant international cabling standards. It is now included or will be soon included. And finally, here is a summary of accepted architectures. Now, according to ISO IEC and TIA standards, the area served by a device is called the coverage area. Multiple devices can share a coverage area. A zone enclosure may also serve one or multiple coverage areas. To ensure support of 5th generation IEEE 802.11ax and future Wi-Fi technologies, a device coverage area or cell size should not be greater than 13 meters or 42 feet. ANSI TSB 162-A specifies square cells no larger than 18.3 meters by 18.3 meters, that is 60 feet by 60 feet. ISO IEC TR 24704 dimensions for hexagonal cells is 12 meters or 39 feet radius or less. The area comprising multiple coverage areas served by a zone enclosure is called the zone area. Different patterns may be used to lay out arrangements for arrangements of hexagon or square-shaped coverage areas with the intent that zone enclosures should be located within their associated grouping of coverage areas. Standards ISO IEC 11801-6 or ANSI TIA-862-B and TIA TSB-162-A telecommunications cabling guidelines for wireless access points, they all provide valuable information on hexagon and grid coverage area distribution patterns. A zone area should range from 72 square meters to 720 square meters, that is 775 square feet to 7,750 square feet, to support a device coverage area radius from 3 to 30 meters, that is 32 to 323 feet. Each coverage area may have multiple SOs, TOs, and direct connections from SCPs to building devices. Solid conductor cables shall be used as well in areas which do not have environmental control, such as raised floors, ceilings, warehouses, etc. Zone enclosures. Now, zone enclosures should be strategically placed throughout a building space to allow quick access to connection points. Coverage areas that are in close proximity to the TR, however, should be connected directly to a distribution point in the TR. Zone enclosures also allow you to pre-wire a work area so that connections to the rest of the network are close to the network users. They also make connection changes within the zone easier and less disruptive because only the cables within a zone are moved, added, or changed. And here are some other key things to remember about the location of a zone enclosure. Remember, a zone enclosure should be permanently affixed. It could be mounted in the ceiling, under the floor, or on the wall. Not too close to the TR. Okay, the MDF or IDF can directly serve a TO if the latter is located within 30 meters of the TR. Site survey can be helpful as well in determining the best ZE location. And Molex recommends obviously a Category 6A zone cabling architecture to properly support PoE applications and others coming applications as well. For remote powering, however, remote powering of LED lighting fixtures, Molex would recommend a 22 AWG Category 5E cable. And remember, planning is essential to make the most of your zone cabling infrastructure. Finally, the size of the zone area should be decreased if more than 96 outlets are required at the ZD to support initial and projected device connections over a 10-year period. Molex would recommend a spare port capacity of 25%. Also, mind your bundle size limitation regarding to PoE standards requirements. Remember as well that each TO, EO, or SO should have a minimum of 2 permanent link connections. There could be exceptions. We will see one in a few minutes, but otherwise you should have 2 permanent link connections. And as far as PoE, high power PoE and UPoE applications are concerned, you may always refer to the module 9 of our training courses, as this may impact as well the design of your zone cabling architecture. Okay, so hope everything is clear so far. What we will now do is to take a look at a simplified design example and see how adding all our different type of applications will impact our overall cabling design. Many applications may be included in our design: lighting, voice data, wireless, video surveillance, access control, AV, energy management, and so on, HVAC, digital signage, DAS, and so on. However, to keep our design relatively simple, we will just add a few of them. Then we will create our cabling zones and see the impact on our BOM compared to traditional cabling. Let's start with the location of our telecommunication room and with some of the main things to consider. To start with, the size of the TR should follow the guidelines of the ISO IEC 14763-2 or NCTA 568D. And once we know exactly how many equipment outlets we have, we will obviously be able to determine whether the size of our TR is compliant or not. Now, let's define the total number of work areas. To do so, we will need to define where people are seated and where we have the need for work area outlets. As can be seen on this drawing, we have 8 main areas where people are seated with a total surface of 490 square meters, or 5,274 square feet. And as per international cabling standards, this gives us a minimum of 49 work areas of 10 square meters or 107 square feet each for a minimum of then 98 work area outlets. Let's define each of our work areas. As we have 49 different work areas, we should include a minimum of 98 work area outlets in our design, a minimum of 2 work area outlets per work area. Having now positioned our work area outlets, we have a total of 103 drops or 206 work area outlets for 49 work areas. Our design is then compliant to international cabling standards. Naming conventions, these are our telecommunication outlets, TOs, since they are connecting to a voice or data service. From the telecom room, we can now position and visualize our main cable tray. And then our main cable runs. Here, we then have a total of 5,396 meters of cable or 17,698 feet. This is an average of 26 meters or 86 feet per link, and our longest PL permanent link is 44 meters or 144 feet. Our design is then compliant with international cabling standards. And these are at real scale, so these are not just figures in the air like this, these are real numbers. Now let's position our wireless access points. The ANSI TIA 162-A and the cell grid strategy here will be our guide. In our example, we will need a minimum of 2 grids. However, they are slightly larger than what is needed. As a result, we will adjust our cell grids to the size of our floor. And we can now place our wireless access point. But remember, the first step in a wireless LAN deployment is to ensure that the desired operation begins with a site survey to assess the radio frequency behavior in a specific environment, because many issues can arise in a wireless network due to poor planning and coverage, and it's been discovered that many site surveys are not performed properly, or the site survey sometimes is simply omitted altogether. The grids may be smaller as well to allow for higher data rates or support increased occupancy. Category 6A cabling is deployed to each WAP for higher data rates and increased power delivery. As per international cabling standards, for wireless access points and intelligent buildings, Category 6A is recommended. The use of 2 horizontal links per WAP is also recommended to allow link aggregation. Our cables will follow our main cable trays. And then here we have a total of 163 meters of cable or 535 feet, which is an average of 20 meters or 67 feet per work area outlet. And our longest permanent link is 30 meters or 99 feet, we can say our design is standard compliant. We may now position our AV equipment outlets, and for our design, we have a total of 8 work area outlets to be used for AV applications. Okay, so we made that decision because these are meeting rooms and there is no real need or justification for 2 work area outlets per audio video access point. Our cables obviously will follow our main cable trays, our main cable runs, and in the end we have a total of 402 meters of cable or 1,319 feet. That is an average of 25 meters or 82 feet per work area outlet. And our longest PL is 32 meters or 104 feet. We can say our design here again is standard compliant. Now, we shall add all our equipment outlets to connect our IP cameras. Please also note that we could also have used MPTL connectors for these IP cameras, which would provide additional benefits. Because indeed, as IoT and intelligent buildings continue to converge, more devices are being installed without the traditional RJ45 work area outlet, such as in locations above the ceiling or on the wall. Some good of this include wireless access points, PoE LED lighting systems, AV displays, and IP cameras. Nowadays, more of these devices are designed with built-in RJ45 ports. Okay, so this MPTL here would then replace the conventional work area outlets for building devices only, which allows for these connections to be out of sight, located in the ceiling, or directly within the device. However, please note that this makes more challenging to detach the device. Right, you know the philosophy now. We have our main cables following the main cable trays, our main cable runs. In the end, we have a total of 235 meters of cable or 772 feet, which is an average of 17 meters or 55 feet per work area outlet. Our longest permanent link is 31 meters or 103 feet. Our design is standard compliant. Naming convention here. These are our services outlets as per ISO IEC or equipment outlets as per ANSI TA, since they are connecting to a building device. We can now position our access card readers. We have our main cable trays, our main cable runs. In the end, we have a total of 320 meters of cable or 1,051 feet, which is an average of 23 meters or 75 feet per work area. Our longest PL is 39 meters or 127 feet. Our design is again standard compliant. Some temperature sensors will also be added. Note that many other sensors could also be added to an intelligent lighting system like the CoreSync from Molex. These sensors may include daylight sensors, humidity, smoke, etc. Then this will all follow our main cable trays. We have our main cable runs. In the end, we have a total of 558 meters of cable or 1,831 feet, which is an average of 21 meters or 70 feet on average per work area outlet. Our longest PL is 39 meters or 126 feet. Our design is standard compliant. Finally, let's now position our troughers and some wall lights. Please note that the design of the lighting system must be as well preceded by a comprehensive site survey. There are multiple options to attach intelligent luminaires to an Ethernet network. And for the sake of simplicity here, we will consider one MPTL plug per luminaire. In our design, we have therefore a total of 76 additional single connection points. Our intelligent lighting cable runs will also follow our main cable trace. And here we have a total of 1,638 meters of cable or 5,371 feet. This is an average of 22 meters or 71 feet on average per connection point. Our longest permanent link is 42 meters or 136 feet. Our design is then standard compliant. As per our BOM, we have a total of 76 lighting fixtures, that is 56 2x2 troughers and 20 wall lights. Our design for intelligent IP LED lighting allow for 45 watts per 9 square meters or half a watt per square feet and 100 lumens per watt. This area here on the right side is dedicated to the IP lighting system. We have a total of 4 UPV switches for the time being from Cisco. We have this time chosen the Cisco Catalyst 9300 series with secondary power supplies where appropriate. Each 28-port UPV switch may have a power budget of up 1,440 watts with the addition of an extra power supply. All troughers and other luminaires are attached to these horizontal patch panels here on the right side in the middle of this cabinet. The middle rack here is our patching zone. This is where all our remaining applications are distributed, such as network data, AV, access control, WAPs, IP cams, and so on. Each port of these patch panels are attached to work area outlet. Colored icons also have been used and patch codes of different colors as well to easily identify each application. And finally, here on the left, top left corner, this area is our active equipment area. Conclusion, for our conventional cabling system design, we will need 3 racks. We will install 8,712 meters of cable, that is 28,577 feet, and we will need approximately 10.4 days of work for 2 engineers on site with 7 hours of work per day. With all of these various applications converging together in a TR, we will need to ensure that they are administered properly as well. And this is why Molex recommends the use of connector icon labels for an easy and quick identification of these different applications. Although less flexible, another option would be to use colored jacks as well. And this table is a summary of our conventional cabling system design, where you can see we have a total active equipment ports of 218, 360 patch panel ports, and we would need a little bit more than 72 hours, effective hours of work for 2 technicians, which is 10.4 days. And for this comparison, we will just consider the installation of the cable itself, not the termination of the patch panels or the work area outlets or the MPTL plug, because there would be no variations between a conventional cabling and a zone cabling, obviously. As far as power budget are concerned, we have 56 troughers 2x2, 45 watts each, and 20 wall lights 15 watts each. This will require a total of 76 UPV switch ports and 2820 watts of power. We may choose the following configuration: 4 Cisco switches, C9300 series, 24 ports, 830 watts each, which gives us 96 ports and 3320 watts of power available. No need then for additional power supplies. This gives us 20 spare ports and 500 additional spare watts for future use. Now, the total number of equipment outlets served is 360, and according to ISO IEC 14763 standard, the size of our TR should be at least 9.6 square meters or 100 square feet. In our design, the size of our TR complies with the international cabling standards, in which we need to install 3 cabinets, 800 by 800 mil, next to each other. However, this might be a little bit tight. Right, let's now see in the following slides what impact a zone cabling architecture will have on our cabling system, as well as on our TR. For this exercise, we will go with an active zone cabling design. This means the majority of active equipment and network switches will be decentralized. So in summary, for this exercise here, we have chosen the decentralized fixture-centric approach. A node-centric approach would have certainly made our design even more power efficient and cost effective. Let's summarize the different options we had for our design, because indeed, as far as PoE lighting architecture is concerned, we had the choice between several options. The centralized fixture-centric one. This architecture is our conventional or the traditional cabling architecture. Then decentralized node-centric. This architecture here is a little bit more cost-effective since it requires less copper cable, as some lighting fixtures and sensors have been daisy-chained. Then the decentralized fixture-centric. This one here benefits from more flexibility since the zone enclosures provide additional area of administration. However, more copper cabling may be necessary. And with this one, the decentralized node-centric architecture, this one would benefit from even more flexibility as well, since the zone enclosures provide additional area of administration. Additionally, the daisy chain approach reduces the amount of copper cables as well. Active zone cabling decentralized, fixture-centric, and node-centric. In comparison with the two previous designs, these two architectures greatly reduce the amount of copper cable, since each zone enclosure is attached to the TR with fiber optic. And the decentralized fixture-centric zone cabling, active zone cabling architecture is the one we will choose to make the comparison with the conventional architecture. And in our design, we will also use MPTL plugs for our LED troughers, and these are considered as building devices. So to start with, let's define our first zone enclosure, ZE or ZE01. We will look at this one in detail. Then for the other ZEs, they will follow with the same pattern, basically. In our Z01, we will have to feed 20 work area outlets, 2 temperature sensors, and 1 card reader, access control, and 1 WAP as well. Each will have double cable runs. For the time being, we will need to install 48 runs. Then in order to cover lighting, we will need to install 12 additional cable runs. These ones will be terminated with an MPTL, unlike the remaining other applications. At this stage also, depending on your design and the type of lighting fixtures to be powered, an alternative would be to consider this 8-port UPE switch from Cisco. And finally, our zone enclosure 1 will be attached to our telecom room with a 6-core fiber optic link. Then all our remaining endpoints will be distributed with category 6A cable runs. That is conventional data and other building applications. And our lighting fixtures as well, for which we could very well use, as we said earlier, Cat5e AWG22 cable. Naming convention. Here, this is our consolidation point, along with our service concentration point, if we refer to ISO IEC, and horizontal consolidation point if we refer to ANSI TIA. Our zone enclosure supports both building devices and voice data devices. Just for this small area, let's do a comparison between a conventional cabling system and a zone cabling architecture. As you can see here in our conventional cabling architecture, we have cable runs from our TR to all our equipment outlets, whereas we have only one fiber optic cable run between our TR and our zone enclosure. The table on this slide is finally a comparison between our conventional cabling and our zone cabling architecture for zone enclosure 1 only. And as can be seen, the length of required copper cable is greatly reduced. Just with zone enclosure 1, we can reduce the length of our copper cable runs by 69%. Another approach would be to dedicate some zone enclosures to data and building devices, and some others to our PoE LED fixtures. This would allow to streamline the capacity of our zone enclosures, network switches, and patch panels, but this would again increase the overall length of our copper cable runs. Let's now continue and complete our active zone cabling design. We will now design zone enclosure number 2. This is for our voice, data, and IoT services. And this is for the distribution of our remotely powered LED fixtures. So the table on this slide then is a comparison between our conventional cabling and our zone cabling architecture, but for zone enclosure 2 only. And here you can see as well that we have again achieved 55% of copper cable savings. Let's now continue again and complete our active zone cabling design. We will now design zone enclosure number 3, and this one here is for our voice, data, and IoT services. This is for the distribution of our remotely powered LED fixtures. And here's the comparison between, again, our conventional cabling and our zone cabling architecture for zone enclosure 3 only. And you can see as well here that we can achieve great savings of 65% on our copper cable. Let's now continue and complete our active cabling design. We will now design zone enclosure number 4. And this here is for our voice data and IoT services. And this is for the distribution of our remotely powered LED fixtures. And the table on this slide is the comparison between our conventional cabling and our zone cabling architecture for zone enclosure 4. Again, you can see here the savings we can achieve for our cable, copper cable. And let's now continue and complete our cabling design, since our all remaining voice data and IoT services, along with our remotely powered LED fixtures, are all located near our main TR. There is no real need to have an additional zone enclosure here. All these devices will be directly connected to the TR. And this is for the distribution of our remotely powered LED fixtures. The table on this slide summarizes the final part of our cabling design. And here's a quick comparison between the two architectures. As can be seen, for this design and situation in particular, the cost savings are substantial, both in time and value. Copper cable lengths are divided by 2, along with the installation time. Space savings in our TR room are also of utmost importance, since they allow the design of our TR to be compliant with international standards. So, key takeaways. Zone enclosures must be in a permanent and easily accessible location. Zone enclosures should be centrally located in the serviced coverage area. They should also not serve more than 96 building system links and should be located at least 15 meters or 50 feet from the distributor in the TR. Also, different grids and patterns may be used. However, their radius should not exceed 13 meters or 43 feet. And finally, MPTL plugs may be a good alternative to service outlets or equipment outlets, but they are only allowed for building devices. So that wraps up this session, and I want to thank you for the time and the opportunity to present today. And I hope this information will really prove helpful. If you want to know more information and have more details about all these technology standards and applications, please do not hesitate to refer to our training courses, which are all available for free on our customer support portal at csp.molex.com.